We start recording. Okay, so today we are just going to be wrapping up stuff with inverse functions. Reminder, your Alex module for intro to inverse functions is due tonight at midnight, and then there I think is one more module on inverse functions. Again, you'll have all of the tools you need after today to do that. I will say these are probably the trickiest part of the last unit we will be doing, at least in my opinion. So if anyone needs any help or has any questions, I have office hours tomorrow and Thursday, and as well, you can always just email me and we can set up a time. Also, your homework will be out by the end of today. I'm just trying to figure out how far we're going to get with other stuff before I figure that out. Any questions on anything before we go ahead and get started? All right. Also, grades should be completely up to date. What your grade is right now is where you are at in the class. Every single assignment has been put in, except I think your knowledge check 5. I need to put in knowledge check 5, but otherwise you should know pretty much exactly where you're at right now. If you have any concerns about that, let me know and we can talk. But okay, if there are no other questions, I will just hop right back into the lecture. Share my screen. Okay. So if we remember, we left off on Monday talking about finding exact value of compositions of trig functions. So hold on one sec. I lost the slide up here. There we go. One sec. I'm so sorry. There it is. Okay. We left off on talking about compositions of trig functions and sometimes with other trig functions. So we did a lot of composing things like cosines with inverse cosines and sines with inverse sines, tangents with inverse tangents. But we started talking about, okay, two different scenarios. What happens if we can't evaluate the angle on the inside, like 6 pi fifths? That's not something nice on our unit circle that we're used to. So what do we do when that happens? And how do we find both solutions? And also what happens if, oh, we're composing a sine with an inverse tangent, or we'll see some other different kinds of inverse trig functions composed with each other in a minute. What do we do then? How many solutions do we have? What does that look like? And in this case, it worked out really nicely because we were able to evaluate 3 pi halves. So we could just take it step by step. Okay, figure that out. All right, now we have our input for tangent. How do we solve for that? We're going to do some more practice with that today. Okay, so let's try these two examples, composing different trig functions with inverses of another trig function. I want to find the exact value. Let's start with the tangent of inverse sine of 3 pi fifths. So let's not focus on what the 3 pi fifths means for now. Let's just start about thinking about tangent of theta. We want to find the tangent of some angle theta. That's essentially what we're doing. Sine inverse of 3 pi fifths will give us what theta is, but we're just trying to find the tangent of theta. So that means that theta is equal to sine inverse of 3/5. We know how do inverses work. We know that that means that we can, if we take the sine of both sides, that these two things will undo each other. So that means that the sine of theta is 3/5. This should look a little bit familiar. What do we know about the sine of an angle theta? Well, we know that sine is the y value over the radius. Remember, we had our thing where the cosine was x over the radius, sine was y over the radius, the tangent was y over x, tangent ended up being the slope. The sine of any angle theta for any triangle is just the y value over the radius. So let's draw a picture. What does this look like? Well, first of all, we need to ask ourselves, what quadrant is this in? Well, our sign is positive, so that means we know it's in quadrant 1 or quadrant 2. But do we know which one? We actually do, and that information is embedded right up here. This right here embeds what quadrant we're working in. And why is that? Well, if you recall, the function sine inverse is only defined i.e. has a range on the interval negative pi over 2 to pi over 2. So the sine inverse function will only give us values in either quadrants 1 or 4 because it's not defined elsewhere. We had to restrict the domain of our original function in order to make the inverse function, in order to make it have an inverse. So sine only has an inverse on the restricted domain of negative pi over 2 to pi over 2, which means by and large that the range of sine inverse is negative pi over 2 to pi over 2. So we need something, a quadrant where sine inverse is not only defined, but has a positive sign. And which quadrant is that? That is quadrant 1. Quadrant 2, sine inverse is not defined, but it has a positive sign. Quadrant 4, sine that's the inverse function for sine is defined. However, signs are not positive in quadrant 4. So we know we're working quadrant 1. So let's draw our picture now. Draw some angle. We know the radius is going to be 3 and the y value, or the radius is going to be 5 and the y value is going to be 3 because it's y over r. Now we just have to solve the triangle right here because we want the tangent of this guy, right? And for tangent, we need both the x and the y coordinate. So we need this remaining guy right here to figure out how to solve the triangle. So it's a right triangle, so we get to use Pythagorean theorem. X squared plus 3 squared equals 5 squared. X squared plus 9 is equal to 25. So x squared is equal to 16, which means x is equal to plus or minus 4. However, our x value we can see here is on the positive x-axis. So x is just equal to positive 4. Putting that in here. Okay, so now we have that figured out. We want to find the tangent of this angle theta, whose sine is 3/5. Saying that one more time, we want to find the tangent of this angle theta here, whose sine is 3/5. And we know we're only working with this one angle because we're working with the inverse function in there. Okay, so the tangent of theta, as we said we're going to try to find up here, is equal to the y value over the x value, which is 3/4. So our final answer is 3/4. Again, we have done this kind of problem before. We've done this kind of problem where we have to set up a triangle and say, okay, we have, say the sine of theta is 3/5 and the cosecant of theta is negative 4/3 or something. We would have to put our information together, solve the triangle. We've done this kind of thing before. The only difference is how we're writing it. And so normally, you know how we'd say something like, oh, such an angle such that the sine is 3/5 and it's in quadrant 2. Instead of giving the information of which quadrant we're working in, it is embedded in this inverse symbol here. That is how we know what quadrant we're working in. Instead of having to give that information separately, just by writing it like this, we embed what quadrant we're working in. Questions on this one? All right, let's do another one then. I want to find the cosecant of tangent inverse of negative 3/4. So essentially we're trying to find the cosecant of some angle theta, where theta is equal to the inverse tangent of negative 3/4. I'm just rewriting it a little bit. It's going to be the cosecant of some angle, because when we take the cosecant of something, we're talking about an angle. The input will be an angle. And in this case, our angle is just the inverse tangent of negative 3/4. So let's solve this piece real quick and see if we can draw our triangle. Taking the tangent of both sides, because inverse functions undo one another. And unwrapping that, it's just the tangent of theta is 3/4. All right, let's draw this picture. If we remember, the function, the inverse tangent function is defined on quadrants 4 and 1. So just like sine, inverse tangent is also defined from negative pi over 2 to pi over 2. And I'm actually going to be careful with that because it does not include those. So we know that our answer is either going to lie in quadrant 1 or quadrant 4. If we recall, quadrant 1 has positive x and positive y values, which will result in a positive tangent because a positive divided by a positive is positive. Quadrant 4, we have positive x values and negative y values, which will result in a negative divided by a positive, which would result in a negative tangent. Our tangent value here, 3/4, is a positive 3/4. So we know we are working in quadrant 1 because that is the quadrant within the range of the inverse tangent function that has a positive tangent. So let's draw a triangle. Tangent, if we remember, is y over x.
Excuse me, I think that it's negative 3/4 instead of.
Is it? It is. Thank you. I don't know why I dropped my negative sign. Thank you. Okay, it is negative 3/4. So if it were positive 3/4, it would be in quadrant 1. However, it is not positive 3/4 because I forgot to write my negative sign down. Thank you for reminding me. So since we're working with a negative tangent, we are going to be in quadrant 4. So let's try again. Let's draw that picture. Some triangle. We know it's y over x. Our y value is 3. Our x value is 4. But notice that our y value is negative because we're working on the negative portion of the y-axis. So that's a negative 3 down there. Now solving our triangle, we've seen this triangle hundreds of times before. To solve for a radius, hopefully at this point we would expect to get that our radius is 5. Cool, that worked out. Now, cosecant of theta is always the radius over the y value, if we remember, because cosecant is the reciprocal of sine. Sine is y over r, so cosecant is r over y, just flipping them upside down, just reciprocating is the fancy math word. So our cosecant is 5 over negative 3, so negative 5/3 is our final answer. Again, you've done this kind of problem before. The only difference is instead of, okay, the tangent of theta is negative 3/4 and you're working in quadrant 4, we're just working with the inverse function, which embeds which quadrant our answer will be in. Questions on this one? All right, these are a little tricky, so let's do one more. I want to find the exact value, again, not using the calculator, of the secant of the inverse sine of negative 4/7. So what am I doing? Well, I want to find the secant of theta, where theta is just some angle that is given to us by sine inverse of negative 4/7. Because again, the input for a secant will always be an angle. Inputs for sine, cosine, tangent, secant, cosecant, and cotangent are always angles. So, and in this case, our angle is just written in a fancy way with an inverse function on the inside. All right, let's work this out. Applying sine to both sides to unravel that inverse function. Sine inverse of negative 4/7, not dropping my negative sign this time, which tells us that the sine of theta is equal to negative 4/7. All right, let's draw a picture. Where we know that the inverse sine function has a range defined in quadrant 1 and quadrant 4, just like we talked about on the last slide. Furthermore, we have a negative sign we are working with here. So which of these two quadrants where the inverse sine function is defined has a negative sign? Well, this has a positive x and a negative y. This has a positive x, positive y. The sine value is talking about, or the sign is talking about our y value. So because our y value is negative, that implies that our sine will be negative. As such, we are working in quadrant 4. So let's draw that triangle. It is sine is equal to y over our radius. So we know we have a 4 here and a 7 here, but this 4 is negative because it's a negative y value. We're going on the negative side of the y-axis. Okay, I want to solve for the secant of theta, which is equal to, it's the reciprocal of cosine, which is r over x. So I need to solve for my x value right here. It's a right triangle. Let's use Pythagorean theorem. X squared plus negative 4 squared is equal to 7 squared. So x squared plus 16 is equal to 49. And then x squared, I believe, is equal to 33, which implies that x is equal to plus or minus the square root of 33. Cool. Now we have to think about, because we took a square root, we had to include both positive and negative. Is it positive root 33 or negative root 33? Well, we're working only on the positive side of the x-axis over here. So it is a positive square root of 33. So secant of theta, plugging that in, the radius is 7, the x value is square root of 33, but this is math. I don't like square roots in my denominator, so I'm going to rationalize by multiplying by square root of 33 in both the numerator and denominator, which leaves me with a final answer of 7 square root of 33 all over 33. Questions on this kind of problem? Remember, the only reason we have one solution as opposed to when we were solving trigonometric equations, we had two solutions, is because we are working with the inverse function in our initial statement of the problem. So the quadrant we are allowed to work in is embedded in the problem. We're about to move on to a different kind of problem where we will need to use inverses in order to solve the equations. However, the inverse is not embedded in the problem, so we will still have more than one solution, and we're going to have to think about that. So on that note, let's try solving some trig equations. We're used to this. This is what we spent pretty much half of our last unit doing, is trying to solve different trig equations. The difference here is that we're no longer working with friendly angles. I may have given you an equation like, okay, solve tangent of theta equals 1. And you could do that because 1 was a nice friendly value that we worked with quite frequently when talking about the unit circle. Or solve sine of theta equals negative square root of 3 over 2. I expect at this point that if I put any well-known value on the unit circle for the abscissa or the ordinate, you'd be able to do it. It would be fine. However, how do we deal with it when we have unfamiliar things that are not nice output values or x and y values on our unit circle, like negative 1.3 and negative 4/3? Well, that's how we have to use the inverse function. And these are a little bit trickier than they look, and we'll see why. So I want to solve these equations on the interval 0 to 2 pi. I want all of the solutions. Let's start with this one. First of all, I will expect that we get probably 2 solutions because that's what we're used to. And we'll see why that works out in a second. Probably 2 solutions. Again, we didn't always get 2 solutions. Like when we were working with angles like 3 pi over 2, that would only result in 1 solution sometimes, but that won't happen a lot here because we're not working with nice angles anymore. All right, I want to solve the equation tangent of theta equals negative 4/3. I don't know any thetas, i.e. angles on the unit circle that have a tangent of negative 4/3 off the top of my head, because those aren't nice angles I've memorized. So the only logical thing I can really do here is get theta by itself, which I now know how to do because I have the tools of inverse functions. So let me do that. I'm going to take the inverse tangent of both sides to get theta by itself. So theta is equal to the inverse tangent of 4/3. Now notice I said use a calculator in your knowledge of inverse trig functions. I don't know the inverse tangent of 4/3 off the top of my head, which is why we're doing this. So I'm going to use my calculator in radian mode to solve this. So doing that, I get that theta is approximately 0.93 radians. Cool. Or negative 0.93 radians. All right. So technically, theta is approximately negative 0.93 radians is a solution to this equation. But we have 2 things to consider first. First of all, is it the only solution? Well, we know it's not because we know that every single trig function has infinitely many solutions. That's why when I said find all solutions, we had to add a 2 pi k to the end. But more importantly than that, is it even in our interval 0 to 2 pi? It's not. Negative 0.93 radians, that's a negative number. That is less than 0. So this isn't even one of our solutions that we want. We know we're going to have two solutions in the interval 0 to 2 pi. This isn't even one of them. However, we need this solution in order to solve for the rest of them. To do that, we have to draw a picture. Let's see how this works. I know here is 0, pi over 2, negative pi over 2, and then we'll say that's pi. We know that the inverse tangent function gives us a solution in either quadrants 1 or quadrant 4. Like we talked about a couple slides ago, quadrant 1 is where the positive tangents lie. So if theta was a positive angle, we know it would lie up here. And if theta were a negative angle, we know it would lie down here. The inverse tangent function spat out a negative angle in radians, so we know we're working with an angle in quadrant 4. We don't know where it is, but we know it's somewhere down here. We know that we have some angle, that's theta, that was our answer. Okay, and I guess this one's easy enough to label. We won't be able to do this on the next one, and it's not technically necessary, but it helps to know the tangent is y over x. So we know that this right here is -4 and this is 3, and that'll end up being 5. Again, it does not matter, but we know that. Okay, so we want all of the angles on the interval 0 to 2 pi that have the same tangent as theta. Again, the inverse tangent will only ever give us one solution to the equation because inverse tangent, we restricted the domain of tangent in order to make it a function. So this will only ever give us one solution. In this case, it didn't give us a solution in the interval we want. So we need to think about that. I know this angle here is a solution. In other words, this angle and all other angles coterminal to it will be a solution. So what does that mean? Well, it means this angle is a solution. It means that angle is a solution. We can keep going around. All of those angles are going to be solutions. But I care in particular about this one because we know that -0.93 radians is between 0 and negative pi over 2. So if I just go around the circle once, it'll give me an answer between 0 and 2 pi. So we could just find the one angle coterminal to -0.93 radians by adding 2 pi to it to get it in the interval 0 to 2 pi, and that will be one of our solutions. So we know that one of our solutions is going to be inverse tangent of 4/3 plus 2 pi. That is going to be one of our solutions because the inverse tangent of 4/3 was -0.93 radians, which we use the calculator to compute. And then we just add 2 pi to it. That's going to be one of our solutions because that angle just gets us an angle coterminal with the -0.93 radians. It's -0.93 radians plus 2 pi. We just run around once. That'll give us an answer less than 2 pi, but greater than 0. So exactly what we want. And then it has the exact same tangent because it's a coterminal angle. And by definition, that's how coterminal angles work. They have all of the same trig ratios. Okay, cool. That's one solution, but we're not quite done. Remember, this will probably have two solutions as all other equations we've solved. So what does the other solution look like? Well, I want another angle that has the same 3/4 ratio here, or -4/3, but that is in a different quadrant potentially. If we remember, what about this angle right here? This is also going to have 3/4, just going straight across like this. However, this is going to be the negative value, but the tangent of that is still -4/3. Y is 4, x is -3, -4/3. If you remember when we drew out solutions to tangent equations in general, that's how they looked. They were straight across like that. And it makes sense. There won't be another solution in quadrant 1 because it'll be a positive x and a positive y value, which will result in a positive tangent. And there won't be a solution in quadrant 3 because we'll have a negative x and a negative y value, which will result in a positive tangent as well, because a negative divided by a negative is a positive. So our other solution will be right here, just straight across like this, and it'll be 4, -3. Okay, cool. We know what it looks like, but how do we compute it? Well, remember, we're just going around 180 degrees like this. We're just going around pi radians. Instead of going around the full 2 pi, we just go around a pi to get that angle coterminal. Similarly, we can also think about the reference angle. Like, we know that this reference angle right here is theta. We know that the reference angle right here is theta. So we could think about just starting at our baseline, going around pi, and then going back the reference angle of theta. So as a result, this angle is just the inverse tangent of 4/3, which is that negative 0.93, and then just plus pi. Instead of going around from negative 0.932 pi, we only had to go around pi to get to the angle with the same tangent. And these, when you plug them into your calculator and get the exact values, are going to be your two solutions. And doing that, we get that this one is approximately 2.21, and this one is approximately 5.35. And you can do an intuition check. Are these two answers between 0 and 2 pi? Visually, does my work make sense? The most important thing for these is always to draw a picture, to think about, okay, here's my one solution given to me by the inverse function. What does it look like? Is it in the range of solutions I'm allowed to have? And if not, how can I find angles coterminal and the other solution in order to get to that point? Okay, these are a little tricky, so let's do another example. I want to find the secant of theta equal to negative 1.3. I don't like secants, cosecants, cotangents. They're nasty to work with. It's much, much, much easier to just reciprocate and work with the reciprocal functions. So instead of working with secant, I'm going to work with the cosine of theta because it's the reciprocal function of secant, which just reciprocating the left or the right-hand side, it is negative 1 over 1.3. Just taking 1.3 over 1 and bloop, flipping it over. Cool. Now, again, I'm going to use inverse cosine in order to solve for theta. Again, this may not give me a solution, but it will give me a solution to the equation that's not in 0 to 2 pi potentially, and it's one I will need to use in order to find the solutions. It could give me one in 0 to 2 pi. And in fact, for cosine, it will, because the only range of values for inverse cosine is 0 to pi. So applying that, I get the inverse cosine of negative 1 over 1.3, which is approximately 2.45. Just plugging it into my calculator. We're allowed to use the calculator for this one. Okay, 2.45 is like that. We're working with a negative angle here. So cosine is negative in the second quadrant. So we know we're working with an angle over here. Cool, because we're working with a negative angle in here. Our cosine is going to be negative. So we know it's going to be somewhere over here, which makes sense because 2.45 is between 0 and pi. So that makes sense. Okay, I'm not going to bother drawing the dimensions of this triangle because it won't make sense and it doesn't really help us, but we know we're working with some angle in quadrant 2. This is the theta we just found, and it is one of our solutions. It works out well. Okay, but now what we want to do is find an angle with the same cosine as this. We know the cosine is the x value, so we want to find the angle with the exact same cosine. The exact same crosses right here. And if we think about it, we can just draw that because that is the angle that crosses this dotted x line at the exact same point. It has the same radius as our angle here. We're thinking only of just like radius 1 on the unit circle. So that radius ray has to stay the same, but which angle has the exact same x value? Cool. Visually, it makes sense that it's this guy. They both have the same x coordinate right here. They don't cross the x-axis, I was going to say, but if you think about this reference dotted line, they have the exact same x coordinate. We don't know what it is. Doesn't matter what it is, but they have the same x coordinate. Tricky part is, how do we calculate this guy? How do we get that theta? Well, we know that 2.45 is going to be one of our solutions because it is from 0 to 2 pi. It works out nicely. We didn't have to do to manipulate it twice like we did over here for tangent. We're only going to have to manipulate it once because we already, the inverse cosine function gave us one of our solutions, which is nice. However, how do we find this guy right here? How the heck do we do that? Well, if you recognize this angle is theta right here, this is the exact same angle, just going the opposite direction. This angle is negative theta. It is the exact same as theta. We're just going the other way to get to it. Okay, so negative theta would be a solution to this equation. However, negative theta is not within the interval 0 to 2 pi. How do we get an angle coterminal to negative theta? Because we know that is the other solution. All of the solutions to this equation will lie on one of these two angles right here. How do we get the angle coterminal to negative theta that is within 0 to 2 pi? Well, how do we find coterminal angles? We add 2 pi. So our solution, we have negative theta here, which is negative 2.45 plus, we want to find the angle coterminal to this. So to do that, I should do a brighter color. We just walk around the circle 2 pi, and that gives us the angle coterminal to that, but within our correct range of values. And you can, again, do an intuition check after you plug this into your calculator and do the math. Does this give me an answer between 0 and 2 pi? The one thing hopefully I will never see is numbers that are less than 0 and greater than 2 pi, because it's easy to check. Is my number within the range? Is it in the interval it should be? And you can do that just by plugging it into your calculator. I didn't plug these into my calculator, this part here, but we know that 2.45 is one of our answers because it was given to us by the inverse function. It is in our correct range. It is a solution. Cool, we're good. We did the checks of, is it from 0 to 2 pi? Yes or no. And is it a solution? Yes, it was given to us by the inverse function. So that one's good. And then we had to think about visually, okay, I want another angle with the exact same x value. That's this angle down here. That is the only other angle with the same x value. And how do I get to it? Well, I could go negative theta around. I could go clockwise theta to get to that point, because that would get me the exact same angle. However, shoot, that's not in 0 to 2 pi. How do I get it in 0 to 2 pi? Well, I add 2 pi. Questions on either of these? Again, these are a bit tricky, so we'll keep doing a couple more examples with them, many of them in word problems, actually. But before we do those, let's do some kind of tricky algebra ones. They look tricky at first, but they're actually not too terrible. So instead of having some angle here, like 4/3 or whatever, I want, or not an angle, an abscissa or an output value of the sine function. I just have 2u. I want to write that expression as an algebraic expression with no trig functions. That sounds impossible, because what I'm asking you to do pretty much is get rid of the secant and the inverse sine and write a function equivalent to this. That sounds a little terrifying at first, but how could we do that? Well, first, let's write this out in English to kind of parse what we're doing. What this is asking us to do is find the secant of some angle theta. That's all it's doing, where we're setting theta equal to the inverse sine of 2u, which to us implies that the sine of theta is equal to 2u. I just got that by applying the sine function to both sides of the equation. And then where our theta is in the interval negative pi over 2 to pi over 2. Now, where did I get that information? Well, it was embedded in the problem. Because the range of my inverse sine function is only from here to here, the theta I'm going to get by computing sine inverse of 2u has to be in that range. Questions on that idea? Okay. I don't really know what to do here other than draw a picture. So I'm going to draw a picture. Notice this is kind of niche and weird, but notice that 2u is just equal to 2u over 1. any number is technically itself divided by 1. So we know that the sine of theta is 2u over 1, and the sine of an angle is always the y value over the radius. So let's draw a picture. Now, which quadrant is this going to be in? Is this going to be in quadrant 4, quadrant 1? Well, good news, we don't actually know. Why is that? Because normally in past problems, like for example, the cosine of -1 over 1.3, we knew that that was going to be in quadrant 2 because it immediately gave us that the output, that the x coordinate we were working with was negative. So we knew what quadrant to put that in. However, down here, 2u could be anything. U could be -1/10, which would land us with a negative sign, but you could also be +1/10, which would land us with a positive sign. So we don't know which quadrant this is going to be in. So for the time being, we have to pretend like it could be in either. There may be more than one solution to this. Turns out for this one, it will work out that there's only one solution. But for now, when we don't know the information, we have to pretend like there could be two solutions. So here's one of the solutions it could be in quadrant 1. And that would be my y value is 2u and my radius is 1. Similarly, my y value could be 2u, my radius 1. Answer could be in either of these quadrants. We're working with the same theta. We don't know which yet, but it turns out does not matter. Okay, so what do I want? I want to find the secant of theta, which happens to be the radius over our x coordinate. Okay, I don't know the x coordinate. I've got to solve for it. How do I do that? Pythagorean theorem. I know my x coordinate is unknown. My y coordinate is always 2u. And then it's equal to the radius, which is 1 squared. Simplifying this down a little bit, x squared plus 4u squared, because it's multiplication, we distribute out the exponent like that, is equal to 1. So x squared is equal to 1 minus 4u squared. Sorry, I'm gonna sneeze. No, I guess I'm not gonna sneeze. Okay. Which implies that x is equal to plus or minus the square root of 1 minus 4u squared. Okay, is it plus or minus? Turns out we are always just working with a positive x coordinate regardless of which of the two scenarios we're considering. So x is just equal to the positive square root of 1 minus 4u squared. Cool. Now I can use this information to find the secant of theta, which is just the radius over this x coordinate. So secant of theta is equal to the radius, which is just 1 over the x coordinate, which is square root of 1 minus 4u squared. We could rationalize this denominator, but in the case of this, I don't think it's really necessary. It would look nastier, and this is just a more simplified way to write it. Again, if it asks you to rationalize the denominator, you should, but a lot of times in cases like this, you can just leave it as is. Now let's think about for a second, why was there only one solution? Well, it's because we only cared about the radius, whose sign never changed, and the x coordinate, whose sign never changed because it was always positive, and radii are always positive. So regardless of which of the two scenarios where we're working with a positive or a negative y value, the secant stayed the same because the secant does not concern the y coordinate. Questions on this one? Again, these look a little tricky at first, but I will 99.9% of the time, if you're struggling with one of these problems, the first piece of advice I'll always give you is to draw a picture and think about what you are doing, because drawing a picture, especially for anything concerning inverses, is pretty much necessary. All right, let's do another one. I want to write the tangent of the inverse cosine of w over the square root of 9 plus w squared as an algebraic expression. I don't know why it says expressing, with no trig functions. Okay, again, this looks really scary, but let's try to draw a triangle because that worked out pretty well last time. So first, parsing this out in English, because this is a lot to think about and that's kind of a big nasty function. I want to pull that apart in English words. I'm trying to find the tangent of some angle theta all this is right here is just some angle where we're just saying that theta is equal to the inverse cosine of w over the square root of 9 plus w squared. So taking the cosine of both sides just to get rid of that nasty inverse cosine, I have that the cosine of theta is w over the square root of 9 plus w squared. And also, my angle theta is in what interval? Well, I am working with the inverse cosine function, whose range is only defined from 0 to pi. The inverse cosine function will never, ever, ever give me an angle outside of that range. As such, we know whatever theta is given to us by this expression here will be in either quadrants 1 or 2, i.e. within 0 to pi. So let's draw a picture. Just like the last problem, we do not know which of the 2 quadrants it is. We don't know what W is, therefore we do not know if this ratio will end up being positive or negative. So let's draw out both scenarios, see if that impacts anything. Here's my first angle theta and here's my other angle theta. The reference angles for these two are the same. Cool. Now what do we know? We know that the cosine of theta is equal to w over square root 9 plus w squared, which recall, cosine is the x coordinate on the unit circle over the radius. Cool. So how should we draw that? Well, that means our x coordinate is w. Doesn't matter which direction we're going in, it's always w. Even if it's not negative w if we think about going in the second quadrant, because it's just w. W could hypothetically be equal to -2. That doesn't mean if this is w here, it doesn't mean we're working with negative w. We're still just working with -2. So regardless of which direction we're going, the x coordinate is w. And then our radius is square root of 9 plus w squared. Square root of 9 plus w squared. Cool. Now let's think about, what am I trying to solve for? I'm trying to solve for the tangent of whatever this angle is, which is the y coordinate over the x coordinate. I have my x coordinate, it's w. I don't know what the y coordinate is, so I have to solve for that. And conveniently enough, we're still working with right triangles, so I know I can use the Pythagorean theorem to do that. And notice we're working with positive y values in both quadrants, which is the unknown we're going to be solving for. As such, again, it does not matter which of the 2 thetas it is. Again, it's going to be the same answer because x will always be w, and whatever y we get out from the Pythagorean theorem will not change based on which of the 2 we're working on. So let's do that. Solving for our missing y value, I know that w squared plus y squared is equal to square root of 9 minus, or is it minus? No, it's plus w squared, quantity squared. That gets rid of our square root on that side. A squaring square root gets rid of it. So w squared plus y squared equals 9 plus w squared. And subtracting a w squared from both sides, I get that y squared is equal to 9, which conveniently gives me that y is equal to plus or minus 3. Is my y value positive or negative? It is positive. We are only working on the positive part of the y-axis, so we can conclude that y equals 3. Nice. So using our expression for tangent theta here, I know that tangent of theta is equal to the y value, which is 3, over our x value, which is w. And your final answer is 3 over w. Questions? All right, we have a few word problems to work through, and then we are actually done with inverses, funnily enough. That felt fast. Okay, so you've seen these kinds of word problems, these modeling problems before. We're just thinking about them in a slightly different context now, but let's pull them apart. So the number of daily sunlight in Laramie can be modeled by this equation right here, L of t, where t equals 0 is the summer solstice. Summer solstice is the day of the year that has the most sunlight. So it makes sense that we're using cosine because we'll have the most sunlight up here and then it'll go down and then we'll have, I forget what the one in the winter is called. I don't even know if it has a name, but the day with the least sunlight here, and then we'll go back up and then we'll have the most sunlight again after the year cycle's ended. So it makes sense that we're using a cosine function because wow, that looks like a cosine wave. Convenient. Math is nice sometimes. Anyways, in the next 365 days, I want to figure out when we will have 13 hours of sunlight in days since the summer solstice. So in how many solutions do we expect, first of all? Well, we expect there to be two. We expect there, let's say this is 13, oopsies. Let's say this is 13 hours right here. We expect there to be one day with 13 hours when we're losing daylight, and the days where we're getting closer and closer and closer to whatever this trough right here is called. I don't know the name of it. And then as we're getting closer to the summer solstice again, where we have the most days of sunlight, we'll have 13 hours again. So like most trigonometric equations, we expect two solutions. So how am I going to solve this? Because I want to solve for t, because t is the number of days. I want to solve for what t has 13 hours of sunlight. How do I do that? Well, L of t gives me the days of sunlight. So I want to set that equal to the entire equation equal to 13 because I want 13 days of sunlight. And then so 13 equals 12 plus 3 cosine. And I'm just going to say theta for now. I'm going to say that 2 pi over 365 is equal to theta, because I don't want to have to think about that complicated, nasty thing in front of my t there. I'm just going to try to solve this thinking about theta first, because theta is much nicer. We do substitution sometimes just to make our life easier. So let's solve for theta. Subtract a 12 from both sides. 1 equals 3 cosine of theta. So cosine of theta is equal to 1/3. Now, at this point in our previous unit, you would say, okay, I want to think about what angles theta on my unit circle have an x coordinate of 1/3. Well, unfortunately, there are no nice angles on our unit circle with a x coordinate of 1/3. Convenient how that works sometimes. But we now have another tool we can use in order to find what angles that is. And that is our inverse cosine function, because now we're allowed to use calculators and inverse functions because we have that as a tool now. So to get theta by itself, I'm going to take the inverse cosine of both sides, or the arc cosine is what that's also called. Okay, so now let's think about our two solutions, because we know there's going to be two solutions to this equation. Inverse cosine of 1/3, I don't know what that number is, and I honestly don't really want to bother to calculate it because I have all the information I need. We know that that's what our angle is going to be, though. If anyone wants to plug that into their calculator and do in radians, cool. I'm not going to do that just yet because I don't care about this number. It's not going to be my final answer. All I care about is that I want to find what angle has a cosine of 1/3. I know that inverse cosine is only defined from 0 to pi, so it's going to land in one of these two quadrants. And I'm thinking about what angle has a cosine of 1/3, which is a positive cosine. Quadrant 1 has a positive cosine, positive sine. Quadrant 2 has a negative cosine, positive sine. So I know that I'm going to be working in quadrant 1 because I'm working with a positive 1/3 right here. So my angle is going to be over here somehow. This is my angle theta. Okay, now I said there's going to be two solutions because there are going to be 2 points in the year where there's 13 hours of sunlight. So I want to find the other angle who has the same cosine as theta. In other words, what other angle also has a cosine of 1/3? Well, cosine is x coordinate, so it's going to be whatever other angle with the same radius lines along that x line. That happens to be this angle right here. Okay, visually, we know that's going to be the other solution. Let's call him theta prime. How do we find theta prime? What is theta prime equal to? Well, remember the reference angle is the same. So this is theta, this is also theta. which means that it's negative theta because we're going down theta, we're getting to the same place, except we're just going, instead of going forward positive theta, we're going backwards negative theta. It gets us to the exact same x value. However, that is not from 0 to 2 pi. It's not going to give us a solution we want. It's going to give us negative days since the summer solstice, which isn't, we don't really care about going backwards. We want to think about going forwards. So how do we find an angle coterminal to this that is within 0 to 2 pi? Well, we walk around 2 pi. We go the negative cosine or the negative inverse cosine of 1/3, because inverse cosine of 1/3 gave us theta. So this is just negative theta. So that is just negative theta. We can label it like that if we want, if it makes us more comfortable. But then we need to walk around 2 pi in order to get us a solution that actually makes sense and is not a negative angle. Questions on what we've done so far? Okay, we're not quite done. Remember, I just solved for theta and theta prime, which is great, but I don't care about theta and theta prime. I care about t. So I want to substitute this back in for theta and for theta prime to solve for t, because I don't care about theta. Theta was just a placeholder so I could think about the problem. I want to solve for t, the days since. So plugging 2 pi t over 365 back in for theta and theta prime, my solutions are 2 pi t over 365 is equal to the inverse cosine of 1/3. Solving for t, this is 365 inverse cosine of 1/3 over 2 pi, which when I plug that into my calculator and rounding to the nearest day is 72. Similarly, plugging in 2 pi t over 365 in for theta prime, I get that 2 pi t over 365 is negative inverse cosine of 1/3 plus 2 pi. And then solving for t, that is 365 times negative inverse cosine of 1/3 plus 2 pi all over, that was very bad, all over 2 pi, which rounding to the nearest day is 294. So those are your two solutions. In other words, 72 days after the summer solstice and 294 days after the summer solstice, we will have 13 hours of sunlight in Laramie. Questions on that? Again, if we had just left our angles as theta and negative theta, it would have given us, our second solution would have given us negative days since the summer solstice, which doesn't really make sense. Again, if you see any of these on homework or on exams, I will be more specific in the sense of the, hey, no negative numbers or only use 0 to 2 pi. But in general, whenever you get a word problem like this, just think, okay, I don't want negative thetas. I don't want things less than 2 pi or less than 0. I want to think about how can I find answers coterminal that are within the principal interval 0 to 2 pi, because we like working within the principal interval. It's friendly. Okay. Yep, we have time for the next one. This time we're thinking about launching a cannonball. So the horizontal distance in feet from a cannon, let me try that again. The horizontal distance from a cannon projectile. Wow, this is written very poorly. I'm so sorry. So pretty much the horizontal distance is given by this equation. The velocity is v0 and the angle of elevation is theta, and r0 is that horizontal distance. If I give you the initial velocity, what angle theta should be used to hit a target 150 feet from the cannon? Okay, programmer aside, there's a lot going on in this problem. You have initial velocity, you have this equation for horizontal distance, you have the horizontal distance you want. Let's see what we can do with this information, plug it into our equation and see what we can do to solve it. Okay, so I'm given that r of theta is going to be 150 because I'm trying to hit a target 150 feet from my cannon, and the horizontal distance is given by r of theta. Cool. I also know I can plug in 80 for V naught, so let's do that. So using that information, 150 is equal to 80 squared times the sine of 2 theta all over 32. I still don't really know what to do yet, but I'm just going to simplify this because I see a lot I can just algebraically simplify. So squaring that 80 in my numerator, that's 1600 times the sine of 2 theta all over 32. And dividing that 32 out, 150 is equal to, I believe, 200 times the sine of 2 theta. And then dividing both sides by 200, I get that 3/4 is equal to the sine of 2 theta. Now your senses are probably tingling from the last unit, like, oh, 2 theta, do we need to use trig identities? Nope. In this case, that would honestly just make this more complicated and we wouldn't really know how to solve it. But we would know how to solve sine of theta equals 3/4. So let's just do another substitution for now, just to make our life easier, and then resubstitute 2 theta back in later. So for the time being, I'm going to pretend that 2 theta is named alpha. So I'm trying to solve the equation, the sine of alpha is equal to 3/4. 3/4 is not a friendly value on my unit circle. I can't just think about, what angles do I know on the unit circle with an x coordinate of 3/4? There aren't any. So I have to use my knowledge of inverse functions instead. Taking the inverse sine of both sides to undo that sign, I get that alpha is equal to the inverse sine of 3/4. Cool. Again, I could evaluate this, but I'm not going to because I don't need to know what that number is yet. So all I'm going to do is now draw my picture. I'm thinking about what angles alpha have a sine of 3/4. Well, no, remember that the inverse sine function is defined on quadrants 1 and 4 from negative pi over 2 to pi over 2. And I'm working with an alpha that has a positive sign. So I know that the inverse sine of 3/4 is going to be somewhere in quadrant 1. I don't know what it is, but I know it's going to be in quadrant 1. We'll call this guy alpha. Cool. Now, I want to think about, I know there's probably going to be 2 solutions, because thinking about how you launch a cannon, there's 2 ways we can make something go a very short distance. For example, we could launch it straight up into the air and have it barely go anywhere, or we could launch it at such a low angle it just does a tiny little hop. This one's a little bit harder to draw out than the last one with temperature, but this one will also have 2 solutions, because if you think about the angle of a cannon, there is this perfect medium where it will just go the furthest distance, but if we go a little bit higher than it, it will go shorter distance, and if we go too low, it will also go a short distance. So this is going to have 2 solutions. Clearly, my inverse sine function gave me one of the solutions. This angle is between 0 and 2 pi. It's beautiful. It's nice. We're good there. However, how do I get the second solution? I have to think about what sine gives us a y value, right? So I have to think about what other angle from 0 to 2 pi also shares the y value with alpha. Well, we've been drawing it this way because we've been working with a lot of examples with cosine, but this is the x-axis. We now want to think about the y-axis. What angle shares a y value with alpha? Well, that would be this guy right here in quadrant 2. Both positive y values. Those 2 angles share a y value. Now, how do I think about computing this? Well, notice that the reference angle between these 2 is the same. When we find these, the reference angle is always, always, always going to be the same. Okay, but clearly alpha is not just my answer twice. That this angle that I want to find here, let's call it alpha prime. That's not alpha. That's clearly not alpha. But notice that alpha plus alpha prime is equal to pi, because we go alpha prime to get to here, and then we go another alpha down to get to pi radians, i.e. back to the x-axis. So I can just solve for alpha prime. So alpha prime is just pi minus the reference angle alpha. And we determined that alpha is sine inverse of 3/4. So alpha prime is just pi minus the inverse sine of 3/4. So our two angles for alpha are this and this. Those are the two solutions to the equation sine of alpha equals 3/4. Questions on how we got that? Okay, we're almost there. We have one last step. Again, we found alpha. We found the two solutions for alpha, but we don't care about alpha. We want to solve for theta. So remember, we said that alpha was equal to 2 theta right here. Let's plug 2 theta back in for alpha, see what we get. So we have that 2 theta is equal to the inverse sine of 3/4. Dividing both sides by 2, theta is equal to 1/2 times the inverse sine of 3/4, which I now plug this into my calculator because I actually care what this number is about 0.424 feet. Cool. Now doing it to my other equation, alpha prime, 2 theta is equal to 1/2 times pi minus the inverse sine of 3/4. So dividing both sides by 2, or nope, that 1/2 doesn't belong there yet. That's the next step. Now dividing both sides by 2, theta is equal to 1/2 times pi minus the inverse sine of 3/4, which plugging that into my calculator in radian mode is about 1.15 feet. So those are your two solutions. Questions on how we did this one? All right, let's try to do one more. Yep, I think we have time for one more, and then we are completely done with inverses. That'll leave us in a nice stopping place. Okay, now I want to think about population growth, because population growth is often really nicely modeled by trig equations. So suppose that the population of a particular species can be modeled by this thing right here, which means that P of T is the total population and T is the time, the unit is in years in this case, during the first 9 years. When will the population size be 4,800? So just to think about what is the period at first, we know that the equation for period, and this is just to help us think about what to do, is 2 pi over b. If you remember, b is this little coefficient right here on the equation. So it's 2 pi over 2 pi ninths, which is just 9. So it nicely works out that we have a period of 9 years, which means the population does its complete rise and fall in 9 years, which, cool, makes sense. We're working with the first 9 years. That's working with the first 0 to 2 pi radians. So we're going to be looking for solutions from 0 to 2 pi radians. Cool. Makes sense. That's what we expected. That's what we wanted. So that means we're going to have two solutions because we are looking from 0 to 2 pi radians. All right. Now that we've addressed that because it wanted during the first 9 years, let's think about picking apart this problem. What am I given? I'm looking for when my population size will be 4,800. So I know I'm going to set this equal to 4,800. And then that's all I really know. So I'm just going to write 4,800 equals 1454 minus 1168 times the cosine. I don't want to work with 2 pi over 9t. So I'm just going to set that equal to theta. Make a little note over here. 2 pi ninths t is equal to theta. Again, we will undo that substitution later after we've done the hard work with our inverses. Simplifying this down, I get that 646 is equal to negative 1168 cosine theta. So the cosine of theta is equal to negative 646 over 1168. This is definitely not a nice ordinate I am used to looking at on my unit circle. I don't know what I know it's going to be an X value on my unit circle, but I don't know what thetas correspond to it. So I have to use my tools of inverses. taking the inverse cosine of both sides, I get that theta is equal to the inverse cosine of negative 646 all over 1168. Okay, so now that I have that, I'm going to draw a picture, see if A, is this solution valid? Is it in 0 to 2 pi like I want it to be? And B, what is the other solution? How do I calculate that? Okay, I know that I am trying to find an angle theta whose x coordinate is this. It's negative. That's all I really care about at this point. Where is the inverse cosine function defined? It's defined in quadrant 1 and quadrant 2. It's defined from 0 to pi. Quadrant 1 has positive cosine, positive sine. Quadrant 2 has negative cosine, positive sine. I'm looking for the quadrant where the inverse cosine function is defined that has a negative value for cosine. That is quadrant 2. So I know my angle is going to lie in quadrant 2, just like so. Okay, I'm not going to label my hypotenuse and x side with the 646 and the negative 1168. It's not necessary, but I want to think about, okay, this is my x coordinate right here. What other angle on my unit circle has this x coordinate? Well, that would be this guy down here. This guy also has a negative cosine, and it's the same negative cosine. If we think about this being my circle right here, those intersect at the same point. They will have the same x coordinate. So we want to think about this. Here's theta. And remember, this is a negative theta. If we think about just going around that way, that's going around theta, that's going around negative theta to get to the same place. And we know that because these two have the same reference angle. But remember, negative theta is not a solution. Theta is a solution because it's from 0 to 2 pi, so we're good with theta, but negative theta is not. So how do I get an angle coterminal to negative theta that is within our allowed range of 0 to 2 pi? Well, I add 2 pi to it. So we have this other angle, theta prime, which is equal to negative theta, which is just the negative of inverse cosine of 646 over 1168. And then I want an angle coterminal to it, which we get by adding 2 pi. Cool. I have my theta, my two values for theta now. I have my two solutions to this equation here. However, I don't care about theta. I care about t. So I'm going to remake my substitution for theta and t and solve for t. So doing that, I get that 2 pi ninths is equal to the inverse cosine of negative 646 over 1168. Therefore, there's a t there. Solving for t, I get that t is equal to 9 times the inverse cosine of negative 646 over 1168 all over 2 pi. When I plug this in my calculator and round to the nearest year, this is going to be the third year. Similarly, substituting this back in for theta prime, I get negative cosine inverse of negative 646 over 1168 plus 2 pi. Now dividing both sides by 2 pi over 9, I get that t is equal to 9 times the negative inverse cosine of negative 646 over 1168 plus 2 pi all over 2 pi, which when I plug this into my calculator, this nasty thing, I get that is approximately year 6. So during the first 9 years, the population size will be 4,800, year 3 and year 6. Questions on this one? Okay, this is good timing because that pretty much wraps up our material for inverses. Next time, we're going to completely shift gears and think about, okay, especially in this unit right here, I've been doing a lot of work with solving right triangles. What if I want to find angles or side lengths of non-right triangles? How can I do that? So we are going to start working on that next time. But in the meantime, make sure to finish your intro to inverse functions Alex module that's due tonight, as well as do the, I think it's just the regular inverse trig functions module that will open after the one is due tonight. I don't know when that one's due. I think it's either Thursday or Friday or something, but I will double check that. Otherwise, I will post the homework as soon as possible. Keep up the good work. We're in the home stretch, so that's good.